Okay, this is my Physics 2 Lab 3 on circuits. And then, so for the intro, this lab is basically examining series and parallel circuits to visualize the impact of resistors and capacitors through the loop rule and current conservation, and then like current conservation, the node rule. And so basically my results are the current in the two resistor, like current is 0.02 amps, and then the time constant is 5.94 seconds. And then here's my basic physics concepts, which this is the loop rule, which is just saying that the voltage of a round trip is zero, and then voltage is just equal to current times resistivity. And then this is calculating resistivity over here. And then here's the node rule, which is the idea that the current going into a node is the same that the current is coming out. And then here's how I calculate capacitance down here. Um, and then here is an example of the resistors in series, which we're going to look at, and then also a resistor in parallel. And then for part one, we're using series circuits. So basically a simple circuit with 1.5 volt batteries. I'm predicting that we're going to have 0.02 amps as our current. And so basically I calculate that by using R total, which is the resistance from the large resistor and the baby resistor, added up. And then I calculate current by doing voltage divided by R total, which is 3 from the batteries. And then the system here is the circuit, batteries, resistors, ammeters, wires, and then the surroundings, which is everything else. And then I1 is reading 0.2 amps, and I2 also read 0.02 amps. And then when you reverse it, it basically just reads negative. And then when I open the circuit by replacing it with a voltmeter, the ammeter now reads 0 amps because there's no current going through, and the voltmeter reads 3 volts because it's just reading the voltage amount from the batteries. And here you can see the online version and then the IRL version that we did. And then when I calculate my potential difference stuff, you can see the actual calculations down here. So like the resistor, baby resistor is negative 0.96, and then the big resistor is 2.04. So basically, I want my total change in voltage to be zero due to the loop rule, and that like is pretty much happening here. Um, and then when I'm calculating the circuit element, so when I put the voltmeter across the 100 ohm resistor, I read 0.02 amps. And then when I replace it with an ammeter in parallel, then the ammeter reading is jumping up to 0.06 amps because I'm not using the resistivity of that resistor anymore. And then here you can just see the calculations of the resistivity of everything using Ohm's law, which is voltage divided by current is equal to resistivity or resistance. Yeah. And then for part two, we're using an RC circuit and charging a capacitor. So basically, we're using a 9-volt battery, 200 cap capacitor, and then 2 light bulbs connected in series. Well, just 1 light bulb at a time. And so with the 10 ohm light bulb, the light starts bright and then dims. And then when the battery and capacitor are disconnected, it also starts bright and then dims. And then with the battery and capacitor connected to the light bulb, it charges at 15.4 seconds and discharges at 15.2 seconds for the 10 ohm. For the 20 ohm, it's 25.9 for charging and 27.5 for discharging. And then basically you can see my prediction here, which is RC, which is the resistance times the capacitance, which is from one of the elementary like physics concepts at the beginning. And then I'm graphing the time here to find the slope. And then I can use that to calculate the time constant, which ends up being 5.94, which is about 6 seconds. And then for the questions. So what if I charged a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor reach full charge? And would this prediction happen in real life? So the ideal model has a capacitor reaching full charge immediately, which is not realistic due to the fact that wires and the capacitor itself have a non-zero resistance that increases the time it takes for the capacitor to reach full charge. And then for conclusion, sources and error. So I used the PhET simulation to do my actual math, even though I also did it in real life. So that doesn't account for the resistance of the wires, ammeter, and capacitor, simulating almost perfect circuit. And then in real life, there is resistance loss to wires, ammeter, and capacitor, which means we're not getting a full perfect circuit, which is why some of the math is off. And then a lack of precision when timing to determine the charge and discharge times of the circuit. And then overall, the lab proves that the node rule is true. A current entering a junction will equal the sum of currents from each junction. And then the loop rule, the difference in potential from a round trip path is zero, which we proved earlier. And then the greater the resistance of a resistor in an RC circuit, the longer it will take for the capacitor to charge and discharge, which is shown by the difference in the 10 ohm and the 20 ohm bulb.